I would now like to introduce the concept of the gradient vector. The definition is that the gradient of the differentiable function of three variables, f of x, y, z, is the vector valued function written grad f or del f. That upside down triangle is sometimes called grad or del, and that's defined by grad f of x, y, z is equal to, it's a vector, and that vector contains all three partial derivatives, df dx, df dy, df dz. Now, if it's a function of two variables, then it just has df dx and df dy. If it has more variables, then it's just a vector that contains all of the partial derivatives in order. Now, we will talk a lot about the interpretation of the gradient in a future video, but I at least want to introduce the concept so that you can do some practice problems computing gradients. So for an example, I would like to compute the gradient of the function f of x, y, z is equal to the square root of x squared plus y squared plus z squared. So essentially, this is the distance function. This function gives the distance of the point x, y, and z from the origin. Okay, we can think about this as being x squared plus y squared plus z squared to the 1/2 power. So what is df dx? Well, df dx in this case is going to be 1/2 times x squared plus y squared plus z squared to the negative 1/2 power. And then I need to take the derivative of the inside. The derivative of x squared with respect to x is going to be 2x. And then the derivative of y squared, which is a constant in this case, with respect to x is 0. And the derivative of z squared, which is a constant in this case, is also going to be 0. So I could simplify this. 2x times 1/2 is just x. And then if I'm doing the negative 1/2 power, that's dividing by the square root of x squared plus y squared plus z squared. So that's df dx. Now I hope that you see that there's kind of a symmetry to x, y, and z in this problem. In fact, if I took the derivative with respect to y appears in the equation in the exact same way that x appears. So there's really no difference between the derivative with respect to x and respect to y other than the variable x. Okay, so if I do df dy, it's going to be 1/2 times that expression to the negative 1/2. The derivative of the inside, where y is now the variable, is going to be 2y. And so I'm going to get y divided by the square root of x squared plus y squared plus z squared. So we can play that game again one more time. And we can get df dz. Okay, again, z appears in this equation the same way. So in fact, the derivative of f with respect to z is just going to be z divided by the square root of x squared plus y squared plus z squared. Okay, so what's the gradient of f then going to be? Well, it's going to be a vector that contains all three partial derivatives. I'll notice that 1 over the square root of x squared plus y squared plus z squared appears in each of those partial derivatives. So I'm going to factor it out of my vector. And I'm left with just x, y, and z. Okay, so the gradient vector in this case, it points outward in the x, y, z direction. But what's interesting about this one is that, in fact, you'll notice that this is the vector x, y, z divided by the length of the vector x, y, z. Okay, so if we take a vector and we divide by its length, it turns out in this case, and this is just special to this case, it's a unit vector. And like I said, we will do some more interpretations of gradients in future videos, so I'll just leave you with just the concept of how to compute the gradient. I now want to move on to second derivatives. Okay, so we remember this from calculus that the second derivative is just the derivative of the first derivative. The problem now, though, is that we, for a function f of xy, we really have two first derivatives. Right? We have a derivative with respect to x and a derivative with respect to y. And so because of that, we're going to have actually four different second derivatives. And I will go through them. The first one is the second derivative with respect to x. And that's what happens when you take the x derivative of the derivative with respect to x. That makes sense. Okay, we're going to take the derivative with respect to x and then take the derivative with respect to x again. That's the second derivative with respect to x. But we could also take the x derivative of the derivative with respect to y. Okay, this is called a mixed partial derivative. So we have d squared f dx dy. Okay, and that's going to say that I'm going to take the derivative with respect to y first. That's the inside variable. And then I'm going to take the derivative with respect to x. Well, in a similar way, we could take the derivative with respect to y of the derivative of f with respect to x. So first I take the x derivative, and then I can take the y derivative. And then I can also do d squared f dy squared. That's the second derivative with respect to y. So I'll take the derivative with respect to y of the derivative of f with respect to y. So in fact, there are four different possible second partial derivatives when my function is a function of two variables. We'll look at some notation, just like we did before. So the second derivative with respect to f is f sub xx. The second derivative with respect to y is f sub yy. Now, if I want to take the y derivative first and then the x derivative, I write f sub yx, which I know is a little confusing, right? Because here y was the inside variable and x was the outside variable. But in fact, when we do this notation, we write f sub yx. That says first take the derivative with respect to y and then x. Or if we want to take the derivative with respect to x and then y, we write f sub xy. And those are different ways that I can notate the four second derivatives, second partial derivatives. Okay, so let's look at this function we looked at before. F of xy is equal to x squared plus 2xy squared minus y cubed. We found the x derivative earlier, and we saw that it was 2x plus 2y squared. And we found the y derivative earlier, and we saw that that was 4xy minus 3y squared. So now let's take the second derivative of f with respect to x squared. So let's take the derivative of this function with respect to x. Well, the derivative of 2x is 2, and then 2y squared is a constant, so the derivative of 2y squared in this case is 0. Okay, now let's take the derivative of the same function, but with respect to y. Okay, so the derivative of 2x in this case is 0, but the derivative of 2y squared is in fact 4y. So x was constant, and y was my variable there. Okay, now let's look at the y derivative. Let's take the derivative of that with respect to x. So the derivative of 4xy, well, that's going to be 4y because x is the variable. And so 4 and y are just a constant. So the derivative of x is 1, leaving me just with the 4y. The derivative of the 3y squared in that case is going to be 0 because I'm taking the derivative with respect to x. And then finally, I'm going to take the derivative of that function with respect to y. Okay, that's going to give me a 4x minus 6y. So here x is constant, So the derivative of 4xy is just 4x, and then the derivative of 3y squared is 6y. And those are the second partial derivatives of f of xy. Now, hopefully at this point, you've noticed something. You noticed that the two mixed partials in this case were equal. They both were equal to 4y. And the question is that a coincidence? And the answer is no, that's not a coincidence. There is a theorem in multivariable calculus, and it says that if both the mixed partials, fxy and fyx, if those are both continuous functions on some disk in the plane, we'll call that D, then those two partial derivatives must be equal. Okay, so if those partial derivatives exist and they're continuous in some region in the plane, then those mixed partials must be equal. And that's kind of nice because if you do the derivatives the way I did, first looking at the derivative of y of the x derivative, and then looking at the x derivative of the y derivative, and you get the same thing, then it's a confirmation that you've been doing these derivatives correctly. Now we will do a little bit more in terms of interpretation of second derivatives in a future video.